Hello pre-calc honor students, here we are with chapter 16 on probability and our introduction, finding sample spaces of an experiment and the probability of an event or either of two events happening. Let's start with an experiment. We're going to spin the spinner and record the results. There we go. Blue or gold. And we'll keep some tallies going, okay? So here we are, spin the spinner, spin the spinner. Go. That's a blue. Spin it again. That's a gold. Spin it again. Ooh, let's spin it faster this time. That's a gold. Spin the spinner again. I'm going to pause now and do a bunch more spins and I'll let you know the results. Okay, so I spun it a total of 12 times. So let's calculate what we call our probability, the experimental probability, the number of successes over the number of trials. Well, we ended up with 2 blues and 10 golds. So we have a total of 12 trials and we had 10 successes. 10 twelfths equals 5/6, which is about probability of, let's give 4 decimal places here, 0.8333. Now, that's called the experimental probability. We did an experiment, we recorded our results, and we came up with a ratio of the ways we want it to happen over the total number of ways it happened. Now, the theoretical or empirical probability of event A is given by m over n, where n is the number of equally likely outcomes in the sample space, and m is the number of outcomes corresponding to event A. So in this case, we basically had in our sample space a blue, a gold, a gold, a gold, and a gold section, and we're just interested in the gold sections, gold, 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 gold. So we end up with 4/5 or 0.8. 0.8 for our exact theoretical probability. Now, why do these two differ? But before that, let's get to what's going on here with m over n. Notice some kids think of sample as a subset. No, the sample space is all the ways an experiment can happen. What are you sampling from? And the top then is called the event space. That's the way you want it to happen. So m will always be less than or equal to n, because n is the number of all total ways it can happen. M is some subset of that. So the ratio then of m over n has to be less than or equal to 1. So now we can have a probability more than 100%. And the other end extreme is 0. No chance of the thing happening. Or from 0% up to 100% if you give probability as a percentage. Now, watch this carefully. If you give me an answer of a probability outside of 1, you could possibly lose all the points on a problem. You must check this concept. Probability is a number between 0 and 1, and it can't exceed that. Why didn't our experimental probability match the theoretical probability? It's not supposed to. What would happen if we did more trials? The experimental probability would approach the theoretical probability, kind of like a limit. It's going to get closer and closer to that as you do more and more trials. So here's our first example. Suppose a die is rolled. Give a sample space for this experiment, then find the probability of rolling a prime number. Okay, so the sample space, make sure your sample space is all equally likely events. Any one of the numbers, 1, 2, 3, 4, 5, 6, that's our sample space. The event we're looking for is a prime number. And that's just 2, 3, or 5. So the probability of a prime equals 3/6 or 1/2. Now, example 1.5 here, I added something in here. Again, a die is rolled. What's the probability of a number rolling a number divisible by 2 or 3? Well, notice that there's some overlap here because 6 is divisible by 3 when you're rolling a die. So is 3. And we have 2 and 4 here in this set. So here's the divisible by 2, and here's the divisible by 3's. Notice that overlap. So when we come up with this probability, if we take the probability divisible by 2, that's 3/6. The probability divisible by 3 is 2/6. And we end up with 5/6, which is wrong. Because as we see, that overlap has to be attributed to. So in our problem here, the probability of divisible by 2 or 3 is going to be the probability of 2 plus the probability of 3 minus the probability divisible by 2 and 3. So we had to take our 3/6 chance of getting an even number plus 2/6 minus the 1/6, and then you get 4/6, which is 2/3, and that's the right answer. A die is rolled. Find the probability of rolling a 3 or an even number. Well, notice how I've drawn the sets separately this time. So the probability of 3 or even equals the probability of 3 plus the probability of even minus the probability of 3 and even. But see, this is impossible. That's 0. Because 3 doesn't overlap with the even set, 2, 4, 6. So you could just take the probability of a 3, which is 1/6, and the probability of even, which is 3/6, and get 4/6, or 2/3. Now, let's see what happened in these two examples, because in one case we had to subtract off the overlap, but in the other case we didn't. It all depends if you have an overlap. So the probability of either of two mutually exclusive events happening, if A and B are mutually exclusive events, then the probability of A or B equals the probability of A plus the probability of B. Now, this mutually exclusive means they cannot occur simultaneously. That is, the probability of A and B equals 0. So when you draw it, you show A and B not overlapping at all. Now, notice what I said before, though. The probability of two events happening, and I should put a little diagram in here for this. The probability of A or B, this is when you have the events overlapping. And that's why you have to subtract off the overlap in our general formula for any two events. If you know they're mutually exclusive, you can simplify the formula. To be or not to be, says Shakespeare. What is the probability of to be or not to be? Here's to be, B. Here's not be, out here. The probability of B or not be. These are mutually exclusive events. So the probability of B plus the probability of not B. Well, clearly this covers everything and it's equal to 1. Something is or it is not. There is no in between. So the probability of not A, we can subtract off and say 1 minus the probability of A. Very handy little formula here. It'll come up in our next example. Here's just an outline of the suits in a deck. 4 suits. 2 of them are black, 2 of them are red. Ace through king in each suit to give you your 52 cards. Now, if the deck is well shuffled, what's the probability of a black ace? So we're pulling out one card, and we just have to figure out how many black aces we have. Well, there's 2 of them out of the 52 cards. So that's 1/26. Not a black ace, we can look at it as 1 minus the probability of a black ace. So it's 1 minus a 26th, or 25/26. That's a lot easier than counting up all those non-black aces. A diamond face card. Well, here are the face cards in diamonds. So that's just a jack, queen, king of diamonds out of all 52 cards in the deck. You can leave it as an unreduced fraction, actually, when you're doing probability. Because many times I want to make sure you've counted up the sample space correctly. Suppose a red die and a white die are rolled. So let's make this the red die. And this is the white die over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And let's make this a chart of their sums. What's probably at the sum of the numbers on the die is 9 through 10. Now some people might say, chart smart, let's just list all the sums. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the sums, and we want 9 and 10. All right, 9 and 10, so that's 2 of the possible 11 sums, 2 11ths. Other people might say, oh no, you have to come up with all the sums. 2, 3, 4, oh, what tedium. But you know, there's some tricks. You notice along the diagonals you get all those. These are all 6s, these are all 5s, these are all 4s, this is a 3. Instead of complaining about the tedium, you could have had it done by now. 8s, 9s, 10s, 11, and 12. There, now we can focus on what we're looking for. Sums of 9 or 10. Sums of 9 or 10. So that's readily done. We can say it's 6 out of the 36 possibilities, or a 1/6 chance. That differs from the 2 11ths. This is bogus. Why is this bogus? These elements are not all equally likely. And if you're going to do the idea of m over n, of counting up the event space and divide by this number in the sample space, you got to make sure that everything in the sample space is equally likely. These are not all equally likely. In this case it is, though, because basically there's a 1/36 chance of any one of these combinations coming up. Suppose you toss a coin 3 times. What's the probability that exactly 2 of the tosses result in heads? You can toss a coin 3 times. So let's use a tree diagram on this one. Tails or heads, and then we split off that into tails or heads, and then we split off that into tails or heads, tails or heads, tails or heads. And each of the leaves of this diagram represents a possible outcome. So you get a total of 8 results. And of those 8 results, we want to see what's the probability that exactly 2 of the tosses will be heads. So let's trace the routes where we get 2 heads. So coming down this way, 1, 2, like that. So there's one route. Then here's another route coming down this way, making the turn here, and then coming down this way. There's another route. I think there's another route somewhere. If we come down this way, 2 heads. There's a head, there's a head. And we only have one head over there, so it doesn't work. So it's basically 3/8 then. 3 out of 8. So that's a nice way of illustrating your sample space with a diagram. Odds are not the same as probability. Odds give a ratio of winning to losing. So the odds of the Packers winning the next Super Bowl are 6-5. What is their probability of winning? So we have 2 events. We have the event of winning and the event of losing. And they are in a 6-5 ratio. So we can think of this as 6x and 5x. Okay? Now you either win or you lose, so 6x plus 5x must equal 1. 11x equals 1, so x equals 1/11th. So the probability of winning equals 6 times x equals 6 times 1/11th, or 6/11ths. Notice now we have a number between 0 and 1. You can't just say the probability of Packers winning is 6. The probabilities are in a 6-5 ratio. Okay? Flange